Okay, so version 8.2 of the Tycho software is now available. There are two key enhancements to look forward to in this release, the first of which is an improved and streamlined photometry module. This is thanks to the feedback from another Tycho user. And the next enhancement is that of the new track confidence algorithm. So it is now better able to distinguish between true and false objects. So with that out of the way, let's go ahead and get started. Okay, so I am going to start off with the photometry module, and the main focus here is to demonstrate how much more streamlined the process is, how much easier it is to generate the photometry measurements compared with the previous version. So I have a data set here. This is of the asteroid named Ivar. In fact, this data set is online. It's available on the Tycho website if you want to experiment with it. So this is night number 1, and I have already calibrated, aligned, and plate solved the images. So if you're not sure how to do that, you can consult the user guide, but I've already done that process just to keep this video short. So I have 122 images here, and I'm going to go ahead and load them into the image viewer. So here is the asteroid. I happen to know it is right here. So I double click on it to center it in the field of view, into the crosshairs, and then after doing that I can right click, choose create marker 1. So this defines the starting location of the asteroid, and then I'll go over to some other image in the sequence and then center the asteroid again by double clicking on it and then choose create marker 2. So this is now a defined path. The motion of the asteroid has been defined, and now we can simply do right click, generate photometry set. So now it's generating the photometry measurements again of night number 1, and if we wanted to, we could go ahead and generate a light curve plot. So here is a basic light curve of that asteroid. Now this is just one night of data, but if we were curious, we could attempt to try to find the period of the asteroid. So these would be the search parameters, click find period, and it comes back with a list of candidate rotation periods. So the first one is 4.72 hours, the next one is 2.359. As you can see here, we have only one valley, one peak, so this is not a bimodal curve here, but the first one here in the list is bimodal. It has 2 valleys and 2 peaks, and so this would most likely be the true rotation period, or at least close to being the true rotation period of the asteroid, because it has that bimodal shape to it. Now again, it's just one night of data. We do not yet have light time correction or HG correction just yet. I'll explain more how to do that in just a brief moment. So let's go ahead and get nights 2 and 3 loaded up. Again, I'm going through this just very quickly to show that it's now a very streamlined process to generate photometry measurements. Now, I am using automatic comp stars, and in reality, you'll probably want to manually define your own. Again, that detail, that information is also available in the user guide on how to do that. But for now, I'm just showing the basic process here. So we now have 2 nights of data have been measured, and now I will load up a 3rd night. So let's go ahead and do that. There are 142 images in the 3rd night, and we can go ahead and load them up here. And now you might wonder, there might be some ambiguity as to which one of these is the asteroid. One way to do that is to show photometry stars. So if it is a photometry star, it will have the rectangle around it. So this makes it quite likely that this is the asteroid. But the other approach is you could animate the frames. So go to animate 50 millisecond. So you can see its motion there. That makes it quite obvious. Another way to do it is go to File, Load Known Objects from the image viewer. So you have now the known object window open, and it's showing 2 known objects in the field of view. So the first one is 1627 Ivar, that's the object we want. The other one is 2018 HG2, and so that's not what we want. So click on the object of interest, and it's showing it here in the crosshairs. So then what you can do is then navigate back to the first image in the sequence, and then go ahead and double click to center it, right click, create marker 1, and then go to another image in the sequence, just get some distance on it, double click, create marker 2. So now we have that motion defined and generate photometry set. So again, very straightforward. Now there is actually a third way to find the object in the field of view. If it is an unknown object, there's a way to do that. And that goes back to having ephemeris information of the object, where you might go to tools, either download observations or use existing observations. So if you had this object that is not part of a known database, then you'd have its observations, and then you'd use the find-orb software to compute its orbital elements attached to the image manager and so forth. But that's for another video. Again, for now, I'm just trying to keep this one short and to the point. So now again, we have these 3 photometry sets, and you'll notice these columns are blank. I'll explain that more in just a moment. But for now, if we go to the graph, you'll notice here are the 3 nights of data. Now we do have, for the second night, it looks like potentially an outlier is here. One way to get rid of it is simply drag a rectangle and choose delete from the menu here. So again, now we have our 3 photometry sets. The data looks pretty good. Now we would really like to apply light time correction and H-G correction. So to do that, you select the objects, or the photometry sets, and then choose apply object data. So this then requires you to input either the number or the name of the asteroid. So 1627, I could type that, or I could type Ivar as the name. Anyway, you then click search, and now you have a result returned, and then you can click OK. Now, if it is an unknown object, there's another way to go about it, using observations of that object. But that's time for another video when I get to that. For now, click OK, and you'll note these columns are now populated with the object data. So I go back to graph, and now you can see that we have light time correction, H-G. Those are now enabled by default because we now have object data applied. So if I go now to find period, then again I can use those search parameters as same as before. Click find period, and now we have 4.796 as the candidate period. And so before it was 4.72, now it's 4.79. And so let's compare that with the published rotation period. So I can go to search octave database. This is a database of known asteroids and published rotation periods. So you will not find every single one in this database, but what we want to do is right click and choose view detail. The other option here, if I have it selected, is to import that object. That would import the measurements from others. I don't want to do that now. I just want to know some of the detail about this object. So this can take a moment to do because it's going out to the internet. The server that has this information can be a bit slow sometimes. So we'll give it a moment. You can see this new window appear, and it's being populated with that information. So again, we'll just give it a brief moment now to finish that. And if it hides in the background, then you can go to the navigation bar here, and it's, in this case, the last window. So I click on that tab, brings it to the front. So the published period is 4.795, and that agrees very much with 4.796. In fact, if you go to what others have determined its period to be, 4.796, 4.795, 4.796. So for us to have determined it to be 4.796, it coincides very well with findings that others have had. The other item of interest, again, you can manually define your comp stars if you want to. That's in the user guide. I'll also have a video on how to do that later. The other nice thing about this is that it also has the ability to auto-save the information. So if you forget to save to repository, so you should always save to repository. whenever you have completed your measurement generation, you can recover from an autosave. So that is now a new feature. It's very handy to have that. So anyway, that's it for the photometry module. So now let's take a look at the new and improved track confidence algorithm. Okay, so the demonstration I have here is to compare the old confidence algorithm with the new confidence algorithm. So I have here a list of tracks that have been extracted from this field of view. So I ran the synthetic tracker on these images and it came back with this list of candidate objects. So the goal is to determine which objects are true and which ones are false. So a false object would be a camera artifact, a hot pixel, or random noise, whereas a true object would be a comet, an asteroid, or some other moving object of interest. So I'm going to start off by sorting the results by the confidence column. And so at the beginning here we have the objects with high confidence, and then we have medium confidence, low, and so forth. So if I double click on a high confidence object, then you can see it here as I zoom in. You can see the animation of the substacks, you can see its motion compared with the background. So this is a true object and accordingly it received a high confidence. Now I can take a look at another one, again another true object here with high confidence. But again, this is with the old confidence routine or algorithm, and so far it's doing okay, but there are, however, several objects, these are all true objects here, that received medium confidence. So this one was ranked as medium confidence. Here's another one, also medium confidence. And more importantly, here is a near-Earth object. In fact, this one, this near-Earth object, it was discovered in this field of view, and ideally we would like for it to have received high confidence, but instead it was medium confidence. So I can double click on it, you can see its animation. So this is a faster moving object than the others I showed. And anyway, this scenario here, we would really just like to see the true objects being high confidence and the false to be low or no confidence. In fact, you can see here we have several false objects here that were categorized as medium. So here is a false object here. Here's another one. So this is just random noise that was given medium confidence. And so what happens is that with more of these false objects showing up as medium high confidence, it simply takes more and more time to go through the tracks to visually inspect and analyze if they are in fact true or not. So let's go ahead now and run it with the new confidence algorithm. So I will run again with compute confidence, and so I will go ahead and go up to the top of the list here. So we have the high confidence and medium and low. So you will notice that every single true object except for one is now categorized with high confidence, including the near-Earth object. It was promoted to high confidence, so it used to be medium confidence, now it is high confidence. So that is an improvement, and there is only one true object that is now medium, and this is a very faint one, so medium confidence is appropriate for that. And also, just as important, no false objects were categorized with medium or high confidence. So they are all low or no confidence for those false objects. So one more example is an extreme example. Here I have a data set where the camera is different, the number of images are different, and so forth. So the camera has a lot of hot pixels. It also has, there's no dithering performed in this data set, and there are also a lot fewer images. So there are only 12 images versus the previous data set had 60, which means that when you have fewer images, you also have fewer samples to reliably determine what is and what is not a true object. So this is again a sort of an extreme example where any algorithm would have difficulty reliably determining what is true or false. So again, we can compare the old algorithm versus the new algorithm. So this is the old algorithm, and as you can see, every object is, in this case, have been identified as low or no confidence. And in fact, there is exactly only one true object in this data set. Everything else is a false object. So the object that we want, I happen to know, is at track number 198. So if I double click on it and zoom in, you can start to see it here. So this is a true object, and it was ranked as low confidence. So now we can go ahead and run again with the new track confidence algorithm. And now you can see, if I scroll up the list, then you see that same object, track number 198, is now categorized as high confidence. So that's an improvement, that we can now pick out the true object in this field of view. Now we do have a few false objects where medium. However, again, this is when you do have hot pixels from the camera that can be tracked, then it can still have some difficulty with that. So certainly pattern noise is much more reduced compared with old algorithm, but if you really want to get rid of these other kinds of false objects, then you would either dither the images or take a lot more of them. Now, if you continue to have an issue with that, the other approach, and this is new in version 8.2, is you can now adjust the sensitivity of the track confidence routine. Now, I would only change this when you really do have an issue with hot pixels or camera artifacts. So if we want to now say low sensitivity, I can click OK, run it again, and now you can see that we have the true object is high confidence and all of the false are low or no confidence. So this is certainly an improvement compared with the old algorithm, which had everything as low or no confidence. Now the other extreme here would be to put it as high sensitivity if you really wanted to detect much fainter objects, but there's no need to do that, especially in this example. So you just have more false objects going through, so there's no improvement there. And really the balanced, I would honestly recommend the balanced approach here. That really does have the best characteristics of all of them. So you have a few potential false objects just in this data set. Again, this is an extreme example because there's no dithering, that the images had no dithering performed at all, and the camera has a lot of hot pixels, and it's just overall not a very clean sensor. So if you do have a cleaner sensor, certainly you will not have any breakthrough like this. So again, extreme example. So now with that having been said, I can present the overall performance of the new algorithm, taken with thousands of different asteroids and thousands of different false objects. And now you can see the overall big picture of how it performs. So again, new in version 8.2 is the ability to specify the sensitivity of the tracker. So we have low sensitivity, high sensitivity, and balanced. So to start off with, the low sensitivity, you might use this if you have a camera with lots of hot pixels or camera artifacts, or you are not able to dither the images, then you might use this approach. However, I would strongly recommend simply using a good dark frame or dithering the images. Again, it's much better to handle these artifacts and hot pixels up front rather than rely on the tracker to deal with them. But if you are unable to mitigate those artifacts or dither the images, then you might use the low sensitivity setting. So as an example, I have collected a database of over 2,500 objects. So 995 of these objects are true objects. These are asteroids, comets, and so forth. and 1,558 of them are false objects. So with the low sensitivity, 27 out of the 995 true objects were falsely declared as false, and one and only one out of the 1,558 false objects were declared as true, meaning it had medium or high confidence. So low sensitivity is very good at suppressing those false objects at the cost of also missing some of those true objects. So keep that in mind. High sensitivity is in the opposite direction. So we have only one out of the 995 true objects were falsely declared as false. However, there were 70 out of the 1,558 false objects declared as true. So you'll have a lot more false objects to deal with. But you might use this if you have a very clean sensor and you simply want to detect as much as possible those very, very faint objects. Now, the balanced approach is what I recommend. It works very great across all data sets, and it had only 3 out of 995 true objects were falsely declared as false, and only 5 of 1,558 of the false objects were declared as true. So it's a very, very good balanced approach, and again, I would highly recommend it as a default setting. But if you have issues, then you might try the other two options. That's it for this video. Thank you for watching, and see you next time.